This is Algebra 2, section 7.5, and this is going to be all about piecewise functions. Now, you may or may not remember a little blast from the past here back in section 2.5, last semester when we were graphing lines. Remember mx plus b? At the end of that section, we talked about piecewise functions. And this whole first page is from section 2.5. We said that a function that is made up of several pieces from different functions. Pardon me if I spelled pieces wrong. I always forget I before E or E before I don't know. So a function that is made up of several pieces from different functions is called a piecewise function. Piecewise function. Okay, a piecewise function may or may not be continuous, meaning if you have 2 or 3 pieces, each piece may connect up to the next piece, or it might not connect up to the next piece. For example, now I'm not going to leave this graph, this is just for demonstration purposes. It might be that I have a graph that has 3 pieces. Well, maybe this piece goes to there, maybe the second piece connects up and goes to there, and maybe the third piece connects up and goes to there. So that one is continuous because each piece connects to the next. But maybe it's such that that second piece doesn't connect to either of them, right? So maybe that first piece goes to here, but then the second piece doesn't start until up here. So you notice right in there, there's a break in the graph. So they don't have to connect up, all right? So that I was just kind of throwing that down. That's not really the graph of this example. So in other words, meaning the piecewise graph, it may have holes or breaks in the graph. Holes or breaks in the graph where one piece does not connect to the next one. Okay, so this would have been an example that we would have done back in Unit 2 because it's just 2 lines. Notice each equation is like an mx plus b. Now you got to dig deep and remember how to graph a line. Remember for mx plus b, if I look at this right here as mx plus b, remember the m is the number in front of the x and the b is the number at the end, right? So you start with your b, your y-intercept. So my y-intercept is 1. And then if I'm going to mark off a slope of 1 from that point, I'm going to go up 1 over 1, right? And remember we said you could go both directions if I'm marking off my slope this direction. So if I were to graph the entire line, right? If I were to graph that entire line all the way across the entire set of axes, it would do something like this. That's just the y equals mx plus b. But when I give it this restriction over here, that says I only want the part of the line when x is less than or equal to 0. Well, right here on the y-axis is where x equals 0. Right here is where x equals 0. If I only want the part of that line when x is less than 0, that means I only want this side of the line. I only want this side when x is less than 0, so I don't want that right side. So I'm going to erase all of the other side. And notice right there at x equals 0, I've got a hole. Because remember we determined that because if it has a little equal sign, then you fill in the hole, right? But like on this one right here, because it just has the less than, it doesn't have that little equal to line, that's how you know you have an open circle. Okay, so the first piece, this x plus 1, is the piece that I have graphed, all right? So now let's go to the second piece. If I were to graph this line, still, think of it as mx plus b, so my b is 1. This time my slope is -3, so down 3 over 1. And again, you can keep marking that off in both directions as long as you want to. So if I were to graph the entire line, right, all the way across, it would be something like this. And I could extend it all the way in both directions. But because of this restriction, I only want the part of the line when x is greater than or equal to 0. Well, again, right here on the y-axis is when x equals 0. And if I want the part of the line where x is greater than 0, then that means I want this side. I want this right side of the line. I don't want the left side of the line. So I'm only going to keep that right side. And in this case, the two pieces connected up. Okay. So what I'm saying is right there where the two pieces come together, they met up at the same place. That may happen, it may not. All right, so that would have been an example that you would have done back in Unit 2. But now that we know a lot more parent functions, right? We know parabolas, we know cubics, we know absolute value, we know square roots, we know 1 over x. So we know a lot of different parent functions. So now graphing piecewise functions can get a lot more fun. And yes, that's a fact. It's not an opinion. Okay. So when I look at this first example, I have two pieces. Notice the first piece right here is a parabola, but the second piece right here is a cubic. Okay, so I'm going to start with the parabola. I'm going to completely ignore the cubic. If I were to graph the parabola x squared minus 2, so parabola moved down 2, and we know for parabolas we mark just kind of an up 1 over 1. So if I were just going to graph the parabola, it would be something like this. All right. Well, this restriction says I only want the part of the parabola where x is less than or equal to 1. Okay, right here is where x equals 1. Let me put it in a different color so you can see it. Right here is where x equals 1. And if I only want the part of the parabola that's less than that, that means less than left. That means I only want this side of that parabola. So I don't want that part that's on the right side. So the green is the piece that they tell me I want. Now I do notice that it says x is less than 1, not equal to 1. So I'll make that be kind of a hole right there at 1. Okay, so now to graph the cubic, ignore the parabola that's there. If I were just going to graph the cubic, x minus 2, notice the minus 2 is on the inside. So I'm going to move this cubic 2 units to the right. And remember, for cubics, you mark an up 1 over 1 in each direction. If I were going to graph the entire cubic graph, it would do something like this. But I don't want the entire thing. This says I only want the part where x is greater than or equal to 1. So let's see. Here's where x equals 1. If I want greater than that, that means I want the right side. So I only want this part of the cubic. I don't want this part over here to the left. So that blue part would represent the piece that they're telling me. So the blue is the cubic, just to kind of give you a little bit of a color coding. And the green is the parabola. So it's a little piece of the parabola, a little piece of the cubic. And in this case, the two pieces met up right there at x equals 1. Okay, great. They didn't have to, but they did. Okay, so look at my next example. So I have two pieces. So let's start with the first piece. This is going to be an absolute value graph. Completely ignore the second piece. So absolute value, 3 to the left, 4 up. And notice the absolute value is opening down because of that negative out in front. So I would have all the way this direction and all the way, if I wanted to extend it on out, I would have all the way that direction. Okay, but this says I only want the part of that absolute value graph where x is less than or equal to -1. I'm going to go green just so you can see it. Here's where x is -1. That hits my graph right there. So I only want the part of that graph that is to the left. So all of this and this that is to the left of that point at -1. So I don't want this part over here on the right. I only want this part to the left. So that green represents the absolute value piece that we're keeping. Okay, so now let's look at the second piece. This one is a parabola, right? So the whole thing is moved up 3. So here's up 3. Notice that negative out in front, so my parabola is opening down. And remember, for parabolas, we mark off that idea of slope. So down 1 over 1, down 1 over 1. So if I were graphing the entire parabola, I would have that whole thing. But according to this restriction, I don't want the whole thing. I only want the part where x is greater than or equal to, you know what, that should say -1. Sorry, let me fix that. That was meant to say greater than or equal to -1. Sorry about that. All right, so here's where x is -1. So if I only want the part greater, that means I want the part to the right. So I only want the part on that side, which means I erase the part to the left. So here's another situation where the two pieces met up. Okay, great. Remember, they don't have to do that. Okay, look at my next example. So this time there are 3 pieces. Okay, let's start with the first one. When you're graphing a particular piece, you ignore the other pieces. So the first one is 2x minus 1. Isn't that just a line? Think mx plus b. So y-intercept of -1. Slope of 2. So up 2 over 1, up 2 over 1, up 2 over 1. So here's my line. So if I were drawing the entire line, it would be something like that. Okay, but I don't want the entire line. I only want the part when x is less than or equal to -2. So go to where x is -2. See where that hits my line right there. I only want the part when x is less than that. So I only want the part to the left, which means I want to erase all of this on the right side. So that green would be the first piece. Okay, so now let's look at the second piece. Notice this is a parabola. Okay, so this parabola is moved 1 unit to the left and 1 down. And this parabola opens up, so I'll do a little up 1 over 1, up 1 over 1. So here's my parabola. If I were graphing the entire thing, something like that. And this time, I want the part of the parabola that is between -2 and 0. Well, here's where x is -2. Here's where x is 0. If I only want the part between there, that means I only want this piece right here. So I will erase everything else. Notice that one had solid dots. You know what I didn't pay attention to was on that green piece, it didn't have an equal to, so that should have been an open circle. There we go. We'll fix that up. Okay, but the pink one has the 2 endpoints included. And then for my third piece, this is just a square root graph that's moved up 1. So square root graph moved up 1 right there. And then it says I want the part of that. Well, if I draw the entire thing, do my up 1 over 1, I have this. And this says I want the part when x is greater than 0. Well, since this is when x is 0, isn't that whole thing when x is greater than 0? So that means I'll keep that whole thing. So in this case, I have 3 pieces and none of them connected up. Okay, that's fine. They didn't have to. All right. Complete each piecewise function to match the given graph. All right, so here's what I'm doing. I'm giving you a graph. And then I give you part of the piecewise function, and I want you to give me the rest of it. Well, notice in this case, I can tell by looking at the graph, and I color-coded it, that first I have a red piece. Notice that's the absolute value graph. Then I have this blue piece, and notice that blue piece is just a horizontal line. So there's my equation. And then I have a green piece, and you see that the green piece looks like a cubic. So there's the green. So I'm giving you the equation. I'm just saying, can you over here on this side give me the boundaries, right? What are the limitations? Well, doesn't that red graph exist everywhere? Here's where x is 0. Doesn't that red graph exist everywhere to the left of 0? So that would be when x is less than 0. And because I can't tell if there's a solid dot or not, if you want to put an equal to, you can. If you can't tell, then you can just go ahead and say it's equal to. All right, then where do I have the blue graph? Well, the blue graph is between x equals 0 and right here at x equals 3. So I'm going to say x is between 0 and 3. And again, if you can't tell, you're welcome to put an equal to on it. And then where does the green graph exist? Well, do you see that the green graph only exists in this area? So that would be when x is greater than 3. Again, since you can't tell if there's a solid dot or not, if you want to put the equal to, you can. Okay? Look at the next one. So on this one, I have 3 pieces. And again, I've got this parabola when x is to the left of 0, right? The parabola. And then in the middle there, when it's between 0 and 3, between 0 and 3. That's where I have that piece of a horizontal line. And then from 3 on out to the right, so when x is greater than 3, that's when I have that upside down absolute value graph. Okay, so let's look at the first piece. Well, what is that parabola? Well, here's the vertex. Doesn't it look like it was moved 2 to the left and 2 down? So if it's a parabola to the left, it's going to be x plus 2 squared. And if it's 2 down, it's going to be a minus 2. Whereas horizontal line, isn't that just y equals some number? And in this case, doesn't y just equal 2? Remember, the f of x is kind of like your y equals. So by writing it this way, you're just saying y equals 2. Okay? And then the third piece is that absolute value graph. And the first thing I can tell is that it's opening down, so there's a negative. Okay? For my absolute value, do you see that the peak of the absolute value, it looks like it was moved 5 units to the right, so x minus 5. And then it looks like it was moved 4 units up, so plus 4. So in the first example, you'll notice they gave me the equation, I just had to give the limitation or the boundaries. In the second example, they gave me these limitations or boundaries, whatever you want to call them, and then I had to give the equation that matched. Okay? So that is section 7.5 that has to do with piecewise.